Welcome to Firebird Tech. As always, my name is Nick. Today, we're going to be looking at the HP 4204A. This is not a new piece of equipment or a new release of a piece of equipment. This actual device here dates from about 1986, so should give you an idea. The design itself for the instrument in question, which I'll get to what it actually is in a bit, dates from about 1968 to 72 was the original release date. Going by HP's marketing documentation from that time period, what data I've been able to gather, is that you see it being touted as the new oscillator from HP from about 68 to 72 is what we get for new marketing material around this device here. I'll get some of the specs out of the way and exactly what it does right now. What is this giant hunk of piece of equipment that is sitting on my bench right now? This HP 4204A is an oscillator. It generates a sine wave. That is its only purpose. It's not a waveform generator. People think oscillator, waveform generator. No. This only outputs one type of waveform, and that is a perfect analog sine wave, as is being nicely displayed by the bit scope behind you. So yeah, that's actually live, by the way. So, to give you an idea. I'll go back to 10. So this just outputs a sine wave. That's all it does. Most people will call me crazy for spending $150 on something that generates a sine wave and only a sine wave. The reason why I bought this for $150 as opposed to, let's say, something cheaper on eBay, there are DDSs or direct digital synthesizers that will synthesize a whole different types of waveforms: sawtooth, cardiac pulses, sine waves, square waves, all that sort of stuff. Why did I pick this over something that's about $80 to $120, roughly almost the same price as I bought for this one to include postage? Why did I go for this 30-year-old instrument as opposed to something that's newer, smaller, more functional? And that's down to build quality and quality in general. The reason why this thing is still $150 on eBay, even though it's 30 years old, is because it's built like the proverbial outhouse, put it that way. It's built strong, it's built to survive, and we'll have a look on the external as well. Not to mention, we'll actually take the lid off and we'll actually go through each of the boards and we'll show just what makes this thing still perfectly calibrated and, well, accurate, even though it hasn't really been touched or anything in 30 years. So, without further ado, we'll now jump into some of the operation of this. So I'm going to keep the screen up behind me. So right now we're just looking at it in a way of just an oscilloscope. So this has 4 decades at the front, so 4 0 to 9 knobs, supposedly, basically, and then we have our range switch, basically sets hundreds of kilohertz, single kilohertz, as well as hertz as well. So that would be 100 kilohertz, you got 10 kilohertz, you got 1 kilohertz, that sort of stuff. So that's basically your decade here. The vernier knob, I haven't actually been able to measure how much this actually changes the frequency, but the idea behind the vernier knob is to offset from the frequency coefficient, basically. As this thing gets warmer, its frequency is going to change. That is, for those wondering, the frequency variancy with temperature is plus or minus 100 ppm per degree C, which is kind of impressive for a 30-year-old piece of equipment. So that gives you an idea. So as I said before, it's 0.2% or plus or minus 1 hertz, whichever is greater, at 25 degrees C. That's its like banner spec. And for what I've been able to tell, it's basically dead on, even though it's 30 years old. It actually, as hopefully I've mentioned before, this $150 piece of equipment I bought off eBay produces a sine wave and is more accurate than the bit scope, which is about a $900 piece of equipment bought from a reputable manufacturer. So go figure. Other things to note about this is that we have an analog amplitude scale. That's one reason why we have the oscilloscope plugged in. So if we can actually correspond what is on the analog graph to what it's actually producing. A little bit of a interesting note about this is that this scale here that you can just see, of course, we'll get closer views of this in a bit when we do the outside tour of this. it's actually in RMS volts, not in peak volts, which is a bit of an interesting thing because most times when you're talking about signal generators, you set the peak voltage. You don't set the RMS voltage. So if I turn this to 5 volts RMS, 5 volts RMS, it's actually generating a 5.2 volt RMS signal, but the actual peak voltage, where'd my mouse go? The actual peak voltage or maximum voltage is like 7.4 volts. So that's just something to note is that, well, you're actually setting on when you're reading the chart, that's actually an RMS voltage, not the peak voltage, which is interesting, cool and interesting. So just some bit a quirk of this little thing. Anyway, this last knob on the side is actually what I refer to as the range switch, I suppose. It's actually called output attenuator. So basically this is what you set to set the max, to set what basically if you turn the amplitude dial to max, what's it going to read. That's basically how this knob works at the end. And of course you have your 3 standard output terminals. Of course these terminals are 19mm apart, which is the standard banana jack width, so you can put banana jack to banana jack leads on there and do that sort of stuff with it, so that's handy. In my notice I have a resistor decade box here. That's because another little quirk of this machine is that this voltage here and this range switch and this amplitude are only good and accurate, I suppose is the best way of putting it, for a 600 ohm load. So when we're reading this off here, this number, this RMS voltage, is only accurate given a 600 ohm load. If we change the load to greater or lesser voltages, or current, sorry, this is not going to be accurate no more. Surprisingly, really nicely enough, because this is HP after all, HP actually gives the formulas to work out what the offset would be given a known load, which is kind of interesting, given a known load and frequency. So, something to know about this little guy. Anyway, so you can see that so I'll get into a bit more of the operation of this guy now. Going by the original marketing photos, I don't think this power switch is original. Because the original ones that I've been able to find actually have a proper toggle-like switch. This one actually has a push button switch, which actually illuminates when it's on, which you may just be able to see there. Again, we'll come up nice and close to these in a bit to talk about the actual overlay of this thing. So basically, it's pretty simple operation. There's not too much really to them, other than you just set what you want here and you get a frequency out. The amplitude is also pretty easy to set because here is just an analog dial. As you can see, as I'm toggling the dial, the graph goes up and down as you'd expect. Of course, there is also this also goes down to very small voltage levels. So this dial here goes between 1 millivolt to 30 volts. So I can make this basically output a 1 volt sine wave or a 30 volt sine wave, or actually 22.5 volt sine wave. So that's kind of what it is. So I think I've got enough about the actual, what this thing actually is and how it all operates. What I'm going to do now is bring the camera up nice and close. I'm going to do a bit of repositioning and everything so we can actually have a really nice close look at the front panel and its operation, and actually showing off how nice this actually thing is, how nice and clean this thing is for potentially a 30-year-old piece of equipment. So I'm going to turn off the camera and we'll come back and we'll be nice and close up to actually have a look at this beautiful piece of 30-year-old Japanese-made equipment. Be good. So this is the front panel of the HP 4204 oscillator, or 4204A oscillator. Alright, so we have our 4 range switches. So again, these are adjustable from 0 to 9, which is pretty cool. We have our actual decade switch here, so kilohertz, so hundreds of kilohertz. When we change our knob, it goes down to 10 kilohertz. As you can see, the decimal point here is moving down to single kilohertz, down to hertz, as in this is 200 hertz now. Or we can go right back up to 200 kilohertz. Okay. The dial, which I may have to do some fancy lighting on. So if we turn that to there, you can see that the dial is here. It's set currently to about 5 volts RMS. Well, now it is set to 5 volts RMS. We'll actually get a bit of view on that for everyone. So there is your dial. So you can see our dial is there, and then just next to it is our output attenuation. So you can read here, this side down here. Again, these numbers here and these numbers here are only valid for a 600 ohm load. So if this is reading 1 millivolt, that's 1 millivolt at 600 ohm load, which is why we have a 600 ohm resistor right here, okay? That just gives you an idea of what this thing actually looks like on the front panel. If we go down a little bit, you can see our output gauge. That actually, again, changes our output. And then we've got our 3 terminals here. So we've got our positive output terminal, our negative output terminal, and our mains earth. Again, this is removed right now because the bit scope is mains reference, and I don't want to go damaging this by hooking that up to there, okay? For those wondering. And my very broken tripod. So, the other thing I was mentioning before about the non-stock switch here, I don't believe this is original. I may put a photo up here somewhere to show you what the original switch would actually look like. It's actually meant to be a non-illuminated toggle switch, but this one is actually illuminated, which I find actually more useful. It's actually a push toggle switch. I don't know if this graphic is also original. This one actually does look like it's either being done by HP or someone who knew what they're doing, because they've actually silk screened in a correct silk screen for this as well. So it may be original, but all the photos I've been able to find of this instrument show an up-down toggle switch, not an in-out push switch. So a little bit curious there. A little bit of a curious beast in that regard. We'll now zoom back out so everyone can have a look at the instrument as it is. Of course, the bit scope on top, just for an average size comparison. This thing is quite big and beefy compared to modern instruments, modern portable instruments. So this piece of equipment is very, very nice for what it is. I'm going to turn off the camera again, and we'll come around, we'll have a look at the back where I think the date code and serial number are for that particular component. It also will show the fact that this is a made in Japan HP. So a lot of the internal components will be marked with the designation of YHP, or Uagawa Hewlett-Packard, which is the Japanese manufacturer for Hewlett-Packard pieces of equipment, until about the late, I think almost the late 90s or early 90s, before Japan stopped manufacturing HP pieces of equipment. There are some pieces of Keysight and Agilent equipment that are still made in Japan, and of course other places like the US. Not everything is made in China. This is not a made in China piece of equipment. So that's another reason. So anyway, I will turn off this camera and we will go around to the back panel. Alright, so we are starting at the back left hand side of the instrument. So you can see here, this is of course a 230 volt device. This actually has a switch under it if you're wondering. The fuse, for some reason, is actually a 115 volt fuse, not a 240 volt fuse, but anyway. It's really interesting that because this is using an RC oscillator, it's not a crystal oscillator that they've turned into a sine wave or something along those lines. It actually uses the line voltage of the mains, as you see here, to actually generate the frequency. It actually uses that as just like a secondary reference. So you can see here, it says 115 to 230 volts, plus or minus 10%. So you can work out what that actually what this would run on. This helps to basically keep it accurate. And then the other side of this is 48 to 66 hertz. Most devices will also say 50 or 60 hertz. Again, because this is used somewhat to actually generate the reference signal, this has to be within a pretty fine margin to make it work. But again, it's a pretty generous range, so you're not too worried about it. Again, 10 VA is its maximum power consumption. Now, if we have a look at the transformer, you can see that it has a serial number on it, 4204. That's the part number. That's actually a serial number for the part. And you can see here it has 8601. I wonder if that means the first week of 1986. That does seem to be roughly when this was made, given some of the internal components that we'll have a look at in a little bit as well. We'll also designate a year of about 1984 to 1986, somewhere in that ballpark. So it's not one of the oldest of this unit. As I said, this unit was first released in 1968 to 1972, so it's not the oldest of this sort of unit, but I don't think many of these things were made. So if we sort of have a bit of a, sorry, I'll do that. So if we scroll this thing over somewhat, as I said, it's a big hunking beast, and zoom into the label, the actual naming label, and put that back in focus, you can see how it's read Yokogawa, I'm probably pronouncing that incorrect, Hewlett Packard, and then the serial number, and then made in Japan. So it's not a cheap piece of equipment. Labor in Japan is very expensive, parts from Japan are very expensive, particularly when we're talking 1968 or 72 or even 86 when this was produced. This is not a cheap and cheerful component. This is not a cheap and cheerful oscillator. This is made to last. That's the biggest thing. This thing is made to last. So you can see here the serial number 1908J06113. I'm not 100% sure of all of the designation, what this actually means, but I'm pretty sure this is somewhere in the region of, yeah, about 5,000 or 6,000th unit made. So it's about 6,000 and change for the serial number, I think, given some of this stuff here. So not exactly common instruments, considering only 6,000 of these things were, well, as far as we know, this is a 6,000th odd unit. So not huge production levels when you consider, let's say, modern equivalent to this that are made in the millions or hundreds of millions. So yeah, it's something to think about. So I'm going to scroll back a little bit and get you guys back in focus. And I'll also show you, like, this is the sort of thing you won't see on a modern instrument. There isn't just, I don't know if you guys can see that, there isn't just front carry handles. Are we in focus? Yes. So there isn't just front carry handles here. There's also fold-out carry handles as well on the side that fold out to the top. But what's really interesting is if you push them up a little bit, they actually lock into place. They don't actually come out. You actually have to click them down and out, and then they'll rotate. There's actually a detent in there to prevent it. So when you click them up and move them away from here, they actually lock into place. It's an interesting little detail you wouldn't see in a modern piece of instrument. Not to mention every little panel is Phillips heads screwed on by hand. Again, denoting to the quality of this piece of equipment. The other thing to just quickly show is that the bottom of this thing, which we will get back for a little bit, is extremely clean as well. So it's an extremely clean unit. The tilting bale still perfectly works as it was intended. It still works just as well as the day it was made. So, again, I'm going to reposition the camera for a third time, and we'll have a look at the internal layout of this beautiful piece of equipment. All right. Okay, sorry for the handycam, guys, but my tripod just broke. So anyway, this is the internals of the HP 4204A. As you can see, it's very classic, traditional 60s, 70s, 80s electronica. Everything is beautifully laid out. So you've got power supply over here with this board here, your amplifier, your oscillator, your range capacitor. Under this metal case, which I'll take off in a few seconds, contains all of the resistors for this stuff, which is just kind of something I'll definitely get a close-up on. But the thing that I want everyone to remember is that this thing has had a few fixes. You may be able to see in there that these two capacitors and one way down there have been replaced. This is obvious because it's so old. As we go through, you can see that how clean this thing is. This is a 30-plus-year-old piece of test equipment, and it's still like crystal clean at the bottom. There's very little dust. Everything is just like nice and clean. Even like the meter markings haven't even got dust on them. It's just gorgeous, gorgeous stuff. One thing I'd love to have a look at is how they do the indentations in here. You can see that there's little wheels in here. You can see that there's little wheels in here. And when I turn them, there's little levers underneath that are spring-loaded, which allows them to actually be detents. What I'll do is I'll grab a light so you can see that a little bit better. But you can see that there's little spring levers and the flower-style sort of like indented wheels, which give it these beautiful, clunky detents. So you can see that in there, hopefully. It's just these beautiful, big, clunky things. And the other detents in here as well. This is the kilohertz to hertz range. If we have a look at how that's done, it's all passive controls. And like the little resistor that's on the side that's been hand soldered from the two pieces. All this stuff is beautifully made and hand done all the time. Every piece of this would have been handmade by someone or hand soldered by someone. It's like, this is the reason why you buy a piece of equipment like this. Okay, it's 30 years old, but I know this is going to last another 30 years without me having to touch anything. Like if we pull out a board, this is the A1 power supply and sit it down. Like, this is what electronics used to look like. Again, as I said, 4 capacitors. So this one, this one, this one, and this one are not original. Obviously, these two aren't original because they don't even fit the original package style. So they don't even have the original packet. They used to be an actual style, and they've replaced them with some nice Nichicon Chemicon caps and done some pretty average soldering on it. But it serves a purpose, and it doesn't really affect the accuracy or performance of it. But you can tell that if we have a look at some of these transistors in here, or regulators, some of this stuff has actually got custom Motorola part numbers that I can't actually research. But this also leads to, if we have a look at this little variable resistor in here, there we go, you can see it has a date code of 84. What I'll do is I'll turn that upside down to make that a bit clearer for everyone. Again, sorry for the handy cam, but unfortunately I don't have a tripod right now. So you can see in there it says 20th week 84. So that's just to give you an idea of a part number of this board particularly. Another example of when this board was made, it may not show up on camera, but I'll try my best. Oh wow, it's actually showing up really nicely on camera. As you can see, it says the 9th of the 7th, 84 as well. On the back of the PCB, it's been hand stamped by someone on the back of the PCB to show that yes, this was checked and proved in 1984. So the date code on the transformer of 1986 again suggests that this was produced in 1984 to 1986 or somewhere in that ballpark. So we'll go through each of these boards and what they actually function as. So you can see here, pretty obviously by the giant capacitors, rated at some pretty big voltages too. Oops, sorry, I'll zoom that out. So you can see that these big capacitors here are both rated for 100 volts. And you can see here, these ones here are rated for 50 volts and 35 volts. This is obviously a power supply, not to mention the discrete little control transistors or regulators. I'm not actually able to 100% guarantee what they actually are. Sorry. So there's a bit of guesswork involved in trying to find part numbers for something this old. But as you can see, even though this board was repaired, it was repaired with some pretty quality components, genuine Nichicon Chemicon caps. Of course, this one has some damage on it. That's not from me, that's obviously from whenever this was transported last. Again, I'm not 100% sure. But the reason why I say that these capacitors, these blue ones here, are original is because that does actually match a lot of the other brands of capacitors that you see inside this. The other thing you'll notice is that there was no CAD back then when they designed this sort of stuff. We're talking 68 when this stuff was originally designed. There was no real CAD or PCB layout program. So all this would have been done by hand on paper. But yet it's really, really cleanly done. And again, this proves the point again. This thing's 30 years old. There's very little dust on these PCBs. Okay, so we're going to put the power supply board back in. As you can see down there, you can see that it says A1 power supply. So each of these boards actually has a label right near the slot. So there you go, see A1 power supply, this one says A3 amplifier, that one says A2 oscillator, this one down in here says A7 range capacitor, okay? So every one of these boards is actually labeled, physically labeled. Sorry about the weird camera angle whilst I get this board back in. There it goes. Pull out the amplifier module and you can again see just how clean electrically and physically these boards are. So this is what I was talking about. These are the original, truly original caps. They're all an OMD brand cap, or capacitor, sorry. But again, just the cleanness. This divider in here divides the media amplifier on this side with the actual oscillator amplifier on this side. So this amplifier here, all this stuff, is for the front panel meter, which is over here. That's what this is for, and that's why there's this shielding bracket between the two. And the way you can tell that is, it says meter 10 volt and 30 volt. So it tells you the difference between the two. And again, each and every one of these boards is denoted by YHP, or Uegara Hewlett Packard, which means every one of these boards was designed in Japan, built in Japan. This whole instrument was made in Japan, which is another reason why it's so well made. And you can again see the Sony branded capacitors, the transistors in here. If it's not Sony branded, it's Motorola branded, like that little component there, the 2N3409 is a Motorola part number. You can't quite see it, but a better example of the Motorola part numbers are like that little guy there. And again, on these two adjustment pots here, we have date codes for 1984, the second week 1984, the one on the right, and the 15th week of 1984 on the one on the left. So that gives you an idea of, again, when this was made. So this is the A3 amplifier module. And I'll just give you this again so you guys can see the part number. And again, 0420470-7023. I'm not 100% sure if this is the design date when this board was designed and laid out, or just like a reference part number. I'm not 100% sure. I gotta get better light on this. So we're gonna put that one back in. But you can see that the 0420473, oops, I'm gonna change my focus length. You can see that that part number on the PCB matches the part number said down there on the title, okay? And note that all these connectors are actually the same, so you can actually put the wrong board in the wrong slot. So that's why I'm only pulling out one board at a time, just to make sure I don't put the wrong board back in the wrong thing and possibly damage things that I don't really want to damage. Because trying to find replacement parts for this would be pretty difficult. So again, just showing off just how nice this instrument actually is. Now, for those wondering how this system works, switch mode power supplies weren't exactly invented or weren't exactly commercially viable, particularly for precision instruments, when this thing was made. So you can see that we have our mains transformer here. So we have our mains input, fused transformer. Transformer puts out, for memory, I think it's 110, no, I think it's 23 or 48 volt, no, I think it's like 60 volts AC. And then you can see that there's two pass transistors down there, Q2 and Q3, sorry, Q1 and Q2. And they've also got date codes of the 13th week 84 on them, and they're a Motorola 3-252. Or they're either Motorola or another Japanese brand that I can't pronounce at the moment. But you can see again that everything's been sort of bolted down correctly, everything's got mounts. So now we'll move on to, the amplifier board, we'll now move on to the oscillator board. This doesn't actually generate the RC oscillation. This is simply the oscillations. This actually stabilizes the oscillation. So this basically helps to make sure that the oscillation is as steady and as accurate as it is. Again, some really big capacitors, all original. Again, this looks very similar to what's in the power supply. These blue capacitors that are here, very similar to what's here. Okay, and if we have a nice zoom in on that, if we have a really nice zoom in on that, you notice something very odd. It's marked 1500 MF 16 volts. Now in today's modern capacitors, you might see a marking more like this, 220 microfarad. MF and microfarad are actually the same. When these older capacitors were made, as again this has got a date code of the first week 1980 on it, this wasn't really the common designation for a capacitor. This was. So it's really interesting to see this on an instrument of this age, because I found instruments even older than this still using this designation. So it's very interesting to find this designation in here from a very well-known company of OMD. To give you guys an idea, this sort of capacitor is like a $2 or $3 part replacement to get something of equivalent quality. Sorry about that, my camera just cut out. And again, there's other capacitors in here as well, very high voltage ones like this one here. Again, everything is very well laid out. There's a couple of like more modern looking packages like that TO92 instead of these metal can TO99 packages. And there's some really tiny TO99 packages in here that don't even have markings. These two here, they're marked on the top with a brand, or actually a place of origin, Korea, but they actually don't have any side markings on them at all. So that's a really interesting little unknown part. These ones don't have date. This Motorola part or Mitra part doesn't have a part number on it. You can just see going past that everything is very well laid out, very clean. Again, there's another variable resistor that's measured that has a 17th week of 84 date code on it. All the little diodes in here. All the little tiny diodes in here all actually have markings on them that you can probably read through the screen. So that is our oscillation stabilization board. All right. For those playing along at home, the part number on that is 042047022, and then D-1908. Okay. I'll just lift that up so it's a bit easier to see. There we go, that's going to be a bit easier to see. You can see that that's the part number. And again, all the boards and even like the meters, all the sub-assemblies and everything are all got YHP markings to signify that it's a Uagawa Hewlett-Packard built instrument, not Hewlett-Packard America. Because some of these instruments were built by HP in America. They have the designation of HP, not YHP. So that's just something to think about if you ever find that sort of stuff. What I find really interesting, I haven't been able to find any data about, but there's a little plug down there that may not come up well on camera unless I illuminate it. But there's a little plug down there that's got like 3 little pins, little sub-assembly. I haven't been able to find out too much information about that, why it exists, other than the fact that that little board will actually plug into any one of these 4 slots. I don't know if that actually changes anything, maybe model number or something else I'm not familiar with. But it's just interesting to see that little tiny PCB was made to hook 3 wires up to this range selection switch here, which also has some really beautiful detents in it as well. So it's something you can actually use pretty much blind because you know that you're in the spot. You know you're where you are. Little capacitors soldered off to one side there. Anyway, sorry, I'm just geeking out over the really nice components. So that was our oscillator, and now we're going to have a look at the range capacitor. Probably the simplest board out of all of them. So this is our range oscillator board. I'll do it this way to make it a bit easier to have a look at. So you can see, again, YHP at the top corner, 2 very large variable Miyata variable capacitors, I presume. Again, very clean layout, nothing too odd, but again, just beautiful workmanship. Again, looking at the back, no flux residue, clean. Again, all this would have been hand soldered. I'm not 100% sure if mass manufacture was done on these or they're all hand built. Again, there's another date code on the PCB of 84. I think all these actually have date codes of about 84, all within about a week of each other, really. So there's another date code for those playing along at home. So there's your date code of the 18th day of, so 18th of the 8th, 1984. So this just gives you a really close-up look of just how nice the soldering and all the fact that little curvy traces in here, all these little curvy traces. These all actually look tinned as well, so these would have actually been like strips they would have put down. I don't believe this was actually etched. I think this was hand done. So you can see again that some of these connectors at the bottom are bussed together, some of them aren't, so it's very, very, very nice. So most people will say, well, how does it oscillate? Well, the oscillators themselves are these two very large silver blocks at the back. I haven't actually been able to find any data too much on these, but if I take off, oops, trying not to step on my microphone lead. So let's go back to here. If we take off this metal case, carefully of course, you can see every one of these has got a boatload of precision resistors on them. Okay, so the way I think this works, as most oscillators of the time would have worked, is that we have a couple of very precise capacitors. They're actually marked, the screws are marked C101 and C121, so I presume they are capacitors. Very high precision 4-terminal capacitors, which is again really cool. But again, if we come over to here, this is where I kind of geek out at subassembly, because if we come right in, you can see that all of these are hand soldered all the way around. It's just really nice work, but there's also some very odd markings on some of these resistors. Like we've got 4.444k ohms at the bottom there. We turn it around, there's no markings on that one. Then we turn again, there's 4k, and then we've got 2k. Then we have, where are we at there? So we've got like 13.33k. It's very, like there's some very precision resistors in here. What I've been able to find about these is the fact that they are 0.01% resistors. So if you want to look that up on Mauser, you're talking $1 a resistor. So you can kind of see how this device back in 1968 to 70 thereabouts would have costed $700. Back in 1968 to 72, its launch price was $700. So you can kind of see how that all this would have costed back then. Like even the like this is another thing, something you wouldn't see out nowadays. This is the output attenuator. It has its own shielding. I haven't actually pulled this off myself because I don't wish to. Plus, you need to actually pull it out through the front panel to get it out. You actually need to unbolt it from here. There's 2 screws down there. Unbolt it from its own mount, which is there, and then remove this whole thing that way. It actually comes out the front, which is kind of interesting. So I haven't actually been tempted or anything hard enough yet to actually do that. The vernier scale here, this is what actually changes that very minute frequency. It's just a really nice precision variable resistor. There it is. So there you go. Just a nice little precision resistor. The amplitude resistor, which is way down there at the bottom of the case, is right there at the bottom. It's just a double ganged resistor. So sorry, I'll bring over the light source again so people can see. You see down there, just 2 resistors ganged up, and there's the oops. So there's that other resistor. Sorry, the light's a bit bright. So again, even the meter is high quality. Custom branded by YHP as well. So on the front, just in the corner, you may just be able to see it through the glare. It's actually marked YHP as well. So everything in here is either designed, manufactured, or contracted by Yokogawa Hewlett-Packard. So the next thing I'm going to do is I'm going to take off the bottom cover, and I'm going to show you the underside, the underneath of this, to again show you just how nicely everything is even bound. Because even down here, there's little zip ties holding cables together. That zip tie I don't think is original, but even the really clean solder on the transformer and all that sort of stuff. You can see that this wasn't made for your average hobbyist or consumer. It was made for someone who wanted an instrument to last. So anyway, without further ado, we'll come back and we'll have a look at the underside. So before we start with the bottom case, as you can see, well, the bottom section, just want to point out something that I actually haven't noticed before now, before actually properly pulling apart, is that the feet on the bottom of the case, all four of them are branded with the HP logo. All four of these guys. So even the feet, they were proud enough to put their name on. So these actually hold the tilting bail as well. They hold the tilting bail up in here. But even the little feet are branded with HP. It's like, okay. So that's just kind of a little tidbit of information. But we can see as we move around the... yes, I fixed my tripod in the preceding time. Anyway, so you can see that everything's very cleanly done. Again, that's the theme going through this entire piece of test equipment, is that everything is done for a reason, everything's very clean. So you can see the mains comes in here, goes through this cable, up to the switch, comes back, sorry about the cutout, and then comes to here and does the things it needs to do with the power supply and all that sort of stuff. So everything in here is just beautifully, beautifully made. You can see, I don't know if that comes up on camera, but there's little beads here. We'll zoom in on that. We'll zoom all the way in on that, and then we'll... So you may be able to see, you should be able to see, little tie points here and here and here and here. There's a single little bit of cable that runs around that's tied and knotted around up here, and also continues up all the way up this cable that goes to the range select switch. It's like, also each one of these boards is individually grounded to the chassis. There's a couple of support components here, but just everything's nice, neat, purposeful. It's just a good quality board. Board layout. You can also see down here, all the way down there is the two transistors on this other pass transistors. They're on little boards by themselves. So Hewlett Packard was thinking, or Yuagawa Hewlett Packard was thinking, when they made this device, that these guys were going to get hot. So they didn't just mount them solid on the other side, they've actually electrically isolated them on this side. And they're all perfectly made. Look at the little resistor coming up from the power supply board. The other one of those is coming all the way around. It's just, like, even the biggest thing is like the attention to detail. So you can see right here that there's two little ferrite beads put on there just for a little noise suppression. A little specialized coax over here. If we zoom in on that a little bit more and pull that into focus. This is a little coax. All it's doing is going from here to here. They could have probably done that with wire. No, they decided to use a specialized coax for here. It's the same with, like, there's other little examples of that. There's another coax up here. There's another coax here. There's just little things like that. It's just nice quality. You can see there's a bit of a rat nest going from the underside to the top side, but cables have to go somewhere. The other thing is, like, if we go back up to this little resistor here, this is an underside view of the amplitude variable resistor. They've actually made a little cutout to it. They've specially made a little cutout just for those resistors to poke through. They could have moved this dial up 5-10 millimeters. So I'll put that in focus. So they could have moved this dial, well, in this current position, away from this plate, just so they didn't have to cut it out. No, they decided to cut it out anyway. Like the meter has its own cutout. You can just see the bottom of that there. Everything just is done to make it the best quality meter it can. It's a solid piece of equipment. So what we'll do now is we'll go back to the talk view, and we'll do a bit of conclusion and that sort of stuff. All right. Conclusion time. So hopefully this video has let people know that buying something old like this doesn't necessarily mean you're buying a bad thing. This may explain it. So I hope this sort of gives you a bit of an insight into why people still buy 30, 40, 50-year-old HP and Tektronix scopes and pieces of test equipment, because they still work, and they can still work better than modern pieces of equipment, as we've proven today with the bit scope, an instrument made almost 3 decades ahead of what this is, and this is less accurate than this, so for a similar launch price. So that's just something to think about. Also, this also may help to justify why I bought this over a $120 eBay thing. I may put a photo up here of an eBay listing of what I'm talking about. Why I didn't buy just a $120 eBay DDS device? Because this may only just perform one job, but it performs it exceptionally well. As you can see, it's made between 1984 to 1986, somewhere in that ballpark. I'm more leaning towards 1984 personally. But again, just a beautiful, beautiful, beautiful piece of equipment that I hope people understand now why I went and bought this for $150 versus a modern equivalent for several hundred. So anyway, I think that's enough. I'm rambling as it is. So that is the HP 4204A from 1984. Will be used in future videos, which I hope you will watch. So you can follow me on Twitter, etc. And hopefully you'll see me in the next video. So without further ado, this is Fibo Tech.